Hello all. In this lecture, we will discuss something called radiometric dating. It is possible to estimate the life or ages of biological as well as geological specimen using radioactivity. We know that a particular radioactive nuclide, to attain stability, it undergoes several decays and gets converted into a daughter nucleus. And this happens over, say, thousands or billions of years. And the age of or the how old the specimen is, it is possible to estimate by using the radioactive decay law. Generally, for objects which are of biological origin, we use radiocarbon dating, and we will see how radiocarbon dating is done. In the case of radiocarbon dating, we look at the decay of carbon isotope, which is 14C. Now, how this carbon isotope is formed, that we will see now. We know that cosmic rays are there in the Milky Way, and cosmic rays are mainly comprised of high energy atomic nuclei and chiefly protons. And as the cosmic rays enter the Earth's atmosphere, they collide with nuclei of other atoms in their path, and during the process of collision, they produce a shower of secondary particles. And main secondary particle which is being produced is neutrons. And these neutrons, they react with nitrogen present in the atmosphere, and they form radiocarbon 14C via this process. And this radiocarbon, it actually reacts with oxygen present in the atmosphere, and it gets converted into carbon dioxide. Carbon dioxide which is formed from radiocarbon. So there is ordinary carbon, that is 12C, which is present in the atmosphere, that reacts with oxygen to form ordinary carbon dioxide. But in addition to that, this radiocarbon which is being formed, that also reacts with oxygen to form carbon dioxide, which is formed made of radiocarbon, that is 14C. And plants actually inhale carbon dioxide. So along with the ordinary carbon dioxide that they are inhaling, they inhale carbon dioxide which is made of radiocarbon also. So in plants, a content of radiocarbon is there. Animals consume plants. So radiocarbon enters the bodies of animals too, even human beings also. But as long as the plant is alive, the carbon dioxide content it inhales, that is pretty much a constant, or more or less the radiocarbon content within the bodies of plants and animals, as long as they are alive, that remains the same. But when plants and animals die, they can no longer take in radiocarbon atoms. So the atoms already present in the bodies, they will undergo decay. There is no more intake or replenishment in the content of radiocarbon, only decay happens. And radiocarbon decays with a half-life of 5760 years, and it forms 14 nitrogen, which is a stable element. So looking at the proportion of radiocarbon to the ordinary carbon present in a sample, it is possible to evaluate the ages of ancient objects and remains of organic origin. Okay, this is how we estimate the dating of mummies, cloth, leather, charcoal, etc., and how we understand things about ancient civilization. A problem is given here as an example. Here we are given the activity of 14C in a dead sample to be 13 disintegrations per minute per gram, and 14C activity in a living wood sample is also given. We are asked how long ago did the tree die. Okay. Here for this problem we use the radioactive decay law, where activity of 14C of a certain mass of 14C is in the dead sample is given by R, and the same mass of 14C, its activity in living sample, let it be R0. The activity is governed by radioactive decay law. R is R equal to R0 e raised to minus lambda T. From this you can obtain an expression for T. R0 we know it is given 16 disintegrations per minute. R is given as 13 disintegrations per minute. What we need to know is lambda. We know that the half-life of 14C is 5760 years, and the relation between lambda and half-life is this. So from here you can estimate lambda and thus the years since the tree was dead. So that is estimated as 1.7 into 10 raised to 3 years. We also have geological specimens for which we cannot use radiocarbon dating, because radiocarbon dating is limited to about 50,000 years. By that time, all radiocarbon decays into nitrogen. To estimate the ages of rock samples, we use other isotopes whose half-lives are even larger, and that is how geological dating is done. And this is how the radioactive basically the radioactive decay law is satisfied in any case, and we use the decay series of other elements whose half-lives are even much larger than that of radiocarbon, and that is how we estimate the ages of rocks. Here you can see for geological dating methods, we consider the following decay of the following elements. See, potassium argon method just implies that potassium, radioactive potassium, decays into stable daughter nuclide argon, and the half-life in billion years is given as 1.3 billion years. You can see several other parent elements which can be considered to estimate the ages of such geological specimens. All radioactive nuclei are actually members of 4 radioactive series. The 4 radioactive series are given here: thorium series, neptunium series, uranium series, and actinium series, which end up in these given stable products, and the half-life is also given here. Of these 4 series, neptunium series, they are not actually observable in nature as such, but they have been created in the laboratory and decay has been studied. And actually thorium does not decay to lead in a single step. There are intermediate nuclei. So is the case with uranium, actinium, etc. So we see that if we take Na nuclei of a parent nucleus A, after a period of time, there will be an equilibrium situation where there are successive daughter nuclei B, C, etc. And finally only they end up with the stable product. There are intermediary daughter nuclei B, C, etc. And it is found that the activity which is given by R equal to lambda n, where n is nothing but n0 e raised to minus lambda t, and R is nothing but dn by dt. And activity is fairly constant. That is, Na lambda A is Nb lambda B, which is equal to Nc lambda C. Such a condition is called radioactive equilibrium. That is, these daughter nuclei, they decay at the same rate as they are formed. Such a situation is called a radioactive equilibrium, which happens in the case of such series where there are many intermediate nuclei before thorium gets converted into lead. And as an equilibrium situation is achieved during the decay process where this relation is maintained. That is, activity is fairly a constant. This condition is called radioactive equilibrium. Thank you.